We have come to the last topic of our first chapter. We have already talked about wave functions in position and momentum representation, but we exclusively dealt with the one-dimensional space. We assumed that there's only one spatial dimension, but we know that we live in three spatial dimensions, so we just need to generalize these concepts to three dimensions. Okay, that's what we'll do in this class. So far in this section, we have worked exclusively in one space. One space means one-dimensional space. For example, when we wanted to talk about position, we only had one coordinate. We called it the x-coordinate. Okay, the position was denoted by just this one coordinate. And momentum, we only had one component of momentum instead of three. Okay. Now we just have to generalize this to three spatial dimensions, right? And this can be easily done. So let's look at the eigenvalue equations in three dimensions. Okay. So the eigenvalue equations, we write it like this. For the position eigenkets, the position eigenkets satisfy this equation. X vector acting on get x vector prime is equal to x vector prime multiplied by get x vector prime. Okay. So this vector here means that we are talking about a vector operator with three components. It has three components. Okay. And this x vector prime here means that we need three coordinates to locate the particles. So if you want to specify the position eigenket, you have to give three numbers, the x, y, and z coordinates. Okay, or in this notation, we could talk about x1, x2, and x3 coordinates. Right? So this x vector prime can be thought of as a collection of three eigenvalues, right? One along x direction, one along y direction, and one along z direction. The same thing can be done with the momentum eigenkets, and the eigenvalue equation can be written as p vector acting on get p vector prime is equal to p vector prime acting on or multiplied by get p vector prime. Okay. Again, the momentum operator, it's a vector operator. It has three components, right? And these eigenvalues also have three components. We have px, py, and pz. So collectively, we can simply denote it as p vector prime. Now we can look at the orthonormality relation. In one dimension, we had bra x prime get x double prime is equal to delta of x prime minus x double prime. Here we are talking about three dimensions, so we need three coordinates. Okay, so we denote these eigenkets, these position eigenkets, by get x vector prime, as we mentioned. And the orthonormality relation or the normalization conditions can be written as bra x vector prime get x vector double prime is equal to delta cube x vector prime minus x vector double prime. Similarly, for the case of momentum, we write bra p vector prime get p vector double prime is equal to delta cube p vector prime minus p vector double prime. Okay. Here delta cube stands for the three-dimensional Dirac delta function, and this is how we write it. So delta cube of x vector prime minus x vector double prime is equal to delta of x prime minus x double prime multiplied by delta of y prime minus y double prime multiplied by delta of z prime minus z double prime. So the three-dimensional Dirac delta would be 0 if any of these terms are 0. If any of these are 0, right? For example, we know the property of the Dirac delta. If x prime is not equal to x double prime, then this value is 0. Okay, and if y prime is not equal to y double prime, then this thing is 0. And if z prime is not equal to z double prime, then this term is also 0. Right? So this three-dimensional Dirac delta is 0 even if x prime is equal to x double prime, y prime is equal to y double prime, but only z prime is not equal to z double prime. Okay, even in this condition, the three-dimensional Dirac delta is 0. Okay, so this is 0. This Dirac delta returns value 0 if any of these arguments are non-zero. If any of these arguments are non-zero. Okay. Now here are the completeness relations for the position space. Integral d cube x prime get x vector prime bra x vector prime is equal to 1. Okay. We see that the integration here is over the entire three-dimensional space. Similarly, in this case, the completeness relation for momentum is written like this, and here the integration is over the entire three-dimensional momentum space. Okay. So these are the completeness relations. Now, as before, we can use the completeness relations to expand an arbitrary state get. So we can write get alpha as I, or identity operator multiplied by get alpha, which is written as integral d cube x prime get x vector prime bar x vector prime get alpha. Right? We see that this is now a function of all three components of position. Okay, this is now a function of x, y, and z. In other words, this is a function of x vector prime. We can write this as psi alpha of x vector prime. Similarly, in the momentum space, we can use the completeness relations for the momentum eigenkets, and we can write this as integral ket alpha is equal to integral dq p prime ket p vector prime bra p vector prime ket alpha. Right? This again is the identity operator, or this is the completeness relation for the momentum eigenkets in 3 dimensions. Okay, and here again we have got a wave function which we can denote as phi alpha of p vector prime, phi alpha of p vector prime. Okay, so these expansion coefficients, these are the expansion coefficients. These expansion coefficients are identified with the wave functions psi alpha of x vector prime and phi alpha of p vector prime in position and momentum space. Okay, so psi alpha of x vector prime, this means that corresponding to every position in space, you have a complex number. Corresponding to every position in space, this function gives a complex number. And in order to specify each position, you need 3 numbers. Right? So this means we can expand this as psi alpha of x, y, z. Right? So you put in any specific combination of x, y, and z, that will give one possible position in space, and this wave function will give us a number, a complex number corresponding to that point in space. And we know these numbers are related to the probability of measuring that particle at that point. Okay? Similarly, for the case of momentum space. Now let's look at the momentum operator. Okay, so let's again look at the one-dimensional case first. We know that in the position space, ket alpha is represented by bra x prime ket alpha, or the corresponding wave function. This is what we call the psi alpha of x prime. Okay, and the action of momentum operator on ket alpha was represented by minus ih bar partial derivative with respect to x prime of bra x prime ket alpha. Right? Now this can be directly generalized to 3 dimensions. When we go to 3 dimensions, this ket alpha, as we have seen, is represented by bra x vector prime ket alpha, and we write this as psi alpha of x vector prime. Okay, and the action of the p vector on ket alpha will be represented like this. All right, we see that p acting on ket alpha in the one-dimensional case has just one component. It's a partial derivative with respect to x prime. All right, so when we go to 3 dimensions, this should have actually 3 components. All right, one would be minus ih bar partial derivative with respect to x prime. Here there is only one dimension. If there's another dimension, then there would be minus ih bar partial derivative with respect to y prime. There would be one more component, minus ih bar partial derivative with respect to z prime. All right, now all these components together can be written as minus ih bar, and we have got this operator. Okay, the nabla operator. All right, so minus ih bar nabla vector prime. I think it's also called del vector prime. Okay, so this is usually called as either the del operator or the nabla operator. Okay, so this is just finding the generalization of the partial derivative in 1 dimension to the partial derivative in 3 dimensions. Right, so we see that p vector ket alpha should now be represented by the action of this operator minus ih bar del vector prime on bra x prime ket alpha. Okay, this we can write as minus ih bar del vector prime of this we wrote as phi alpha. This was psi alpha of x vector prime. Okay, there's an x vector prime there also. This is fairly straightforward. Okay, now if you want to find the momentum operator when taken between ket beta and ket alpha, if you're looking for this number, then this is written as, you first write, you have of course an integration over all space. Okay, and then you write the wave function corresponding to this bra beta, which is written as psi beta star of x vector prime. Now you write the operator, the representation of the operator in the position basis, which is written as minus ih bar del vector prime. Okay, and then you write the wave function corresponding to ket alpha. It is psi alpha of x vector prime. Right, now you can reach this result by introducing the identity operators in here in terms of the completeness relation as before, as just like we did in the one-dimensional case. I think we already did this explicitly in the one-dimensional case. Okay, so you already know why there is this integral d cube x prime appearing here. Right, we also looked at the transformation functions in one-dimensional case. Okay, the transformation functions that take you from the position space to a momentum space, or momentum space to a position space. Okay, so these transformation functions are given by, again, in the one-dimensional case we had bra x prime ket p prime is equal to 1 by square root of 2 pi h bar exponential ipx divided by h bar. Okay, now all these will become vectors. So we'll get a factor like this, one factor like this for each dimension. So this would become 1 by 2 pi h bar raised to 3 by 2. That would be the normalization factor. All right. And on the exponential, again, you will get one term for each component. Okay. So this you can write as ip vector prime dot x vector prime divided by h bar. Okay. So we can write psi alpha of x vector prime as this three-dimensional Fourier transform of phi alpha of p vector prime. So this is the momentum space wave function, this is the position space wave function, and they are related by this Fourier transform. All right. Similarly, phi alpha of p vector prime is related to psi alpha of x vector prime by the corresponding inverse Fourier transform. So this becomes 1 by 2 pi h bar raised to 3 by 2 integral d cube x prime exponential minus ip vector prime dot x vector prime divided by h bar. All right. Now we said that this is also the representation of the momentum eigenket in the position basis. And these are the plane waves. These are the plane waves in 3 dimensions. Okay. Now let's check the dimension of the wave functions. In one-dimensional problems, the normalization requirement implies that bra x prime ket alpha modulus squared has the dimensions of inverse length. Right? We can understand this as follows. So we know that these wave functions psi alpha of x prime are given by bra x prime ket alpha. And this has a specific interpretation. Modulus of psi alpha x prime squared, right? Modulus square of psi alpha of x prime dx prime is the probability. It's a probability for finding the particle in a small interval dx prime around the point x prime. Okay. So this is a probability, right? So if I integrate all of this probability over all space, over all one-dimensional space, I should get 1. That's the normalization requirement. Okay. So we should have modulus of psi alpha of x prime square dx prime is equal to 1. All right. Now this has the dimensions of length. This is a number with the dimensions of length, which means that, so this 1 here, it's a total probability, is dimensionless. This is dimensionless. So for this whole thing to be dimensionless, this modulus of psi alpha of modulus square of psi alpha of x prime should have the dimensions of 1 divided by length. Okay, so we can say that psi alpha of x prime modulus squared should have the dimensions of 1 divided by length. Okay, because dx prime has the dimensions of length and we need this thing to be dimensionless. Right? This means that psi alpha of x prime should have the dimensions of 1 by square root of L. Okay, or we say that it has the dimensions L raised to or length raised to a power of minus 1 by 2. Okay, so this is the dimension of the wave function in one dimension. All right. Now we could easily generalize this to 3 dimensions. Okay. If you look at 3 dimensions, we have psi alpha of x vector prime is equal to bra x vector prime ket alpha. Okay. Again, we have the normalization idea, right? The concept of normalization, because we need the probability interpretation. So here, when you normalize this, this would mean modulus psi alpha of x vector prime squared, right? Modulus squared of psi alpha of x vector prime integrated over the entire space has to give you 1. Right? Now this d cube x prime is a volume element in space. It has the dimensions of volume. So this has the dimensions of L cube. That means that this modulus psi alpha of x prime, modulus square of psi alpha of x vector prime should have the dimensions of 1 by L cube. Okay, so we see that modulus psi alpha of x vector prime should have the dimensions of 1 by L cube. Okay, modulus squared has dimension 1 by L cube, so that the whole thing is dimensionless. Okay, this means that psi alpha of x vector prime should have the dimensions of 1 by L raised to 3 by 2, or generally length raised to minus 3 by 2. Okay, so that's if you want the dimension of the wave function, it's given here. All right. With that, we have completed the first chapter of our syllabus, and this was essentially the first chapter in the textbook Modern Quantum Mechanics by Sakurai. We have seen the mathematical formulation of quantum mechanics. We started with the Stern-Gerlach experiment and then motivated the formulation based on the results of these experiments. The concepts are quite new when compared to the classical mechanics you are familiar with. All right. And if you really want to understand, if you really want to get a grasp of the subject, you have to solve a lot of problems. Okay? Just following the theory classes or reading the theory in the textbook alone, this is not sufficient. All right. You really have to solve a lot of problems. You have to solve as many problems as you can. Right. So one strategy is to take some standard textbook and try to solve all the problems given there. Okay, there are some good problems at the end of chapter in this textbook, Modern Quantum Mechanics by Sakurai. Right? And if you want more problems, you can look at this textbook, Quantum Mechanics Concepts and Applications by Zettili. There are a lot of problems in this book. There are a lot of solved and unsolved problems. There are a lot of easy problems as well, which will be quite useful when you want to understand some of the basic ideas. Right? So I suggest that you solve as many problems as possible. Let's now solve a problem. I've taken this problem from an old question paper. Okay. The first part of the problem asks us to determine the form of the momentum operator in the position representation. I think we have already done this in class, so I'll just briefly discuss it. Okay. Now, the second part is to represent the position operator in momentum representation and then calculate the commutator in the momentum representation. So let's take it one at a time. First part asks us to determine the form of the momentum operator in the position representation. Now, the approach in our textbook says that we have to define the momentum operator as the generator of translations. Okay, so momentum operator, the definition that we are taking is that it has to be a generator of translations. Okay, now these translations or these transformations in general, we are talking about translation, for example, is a unitary transformation. We have to construct the translation operator as a unitary transformation. We need this to be unitary because we want the normalization to be conserved, etc. Right? So these are called unitary transformations. Now, in general, an operator for unitary transformation, or let's talk about an operator for infinitesimal unitary transformation. Right. So let's look at the operator for an infinitesimal unitary transformation. All right. So when we say infinitesimal, it means it's very small. All right. So an infinitesimal unitary transformation is very close to no transformation. It's very close to no transformation. No transformation means it's the identity operator. So if you apply the identity operator to a ket, you get again the same ket, no change. All right. But an infinitesimal transformation changes infinitesimally from the identity operator. So we can write it in this form, 1 minus. Any unitary transformation can be written in this form. So we can write it as 1 minus. You will have a factor my I by h bar. This h bar is included for dimensional reasons. This I is included to make this unitary, to make this whole thing unitary. Okay. So and any infinitesimal unitary transformation operator can be written as 1 minus I by h bar. This is common. And then we'll have the generator and a Hermitian operator that generates the transformation. Right? For any unitary transformation, there will be a generator that generates the transformation. And we are interested in Hermitian operators. So if you are including a Hermitian operator here, then you have to have an I here so that the whole operator is unitary. Right? So that's the reason why there's an I here. Right? There's also an infinitesimal parameter of transformation. There will also be an infinitesimal parameter for translations. So this is how we can write any infinitesimal unitary transformation in quantum mechanics. Okay, we write this I here because we want Hermitian operators in here, and we are interested in Hermitian operators. In quantum mechanics, we are interested more in Hermitian operators. All right, and epsilon is an infinitesimal parameter. Now, if you come to translation, right? If you come to translation, we can write the generator or the operator, the unitary operator for infinitesimal translations like this. We can write this as j of dx prime. We can write it as, again, the identity operator minus I divided by h bar. And we need an operator of translations, a Hermitian operator that corresponds to translation. So that's a generator of translations. All right. So whatever appears here, we call the generator of this particular unitary transformation. All right. And the idea that we started with is that momentum is the generator of translations. So instead of g here, I'm supposed to add the momentum operator in here. And epsilon is an infinitesimal parameter, which we write here as dx prime. All right. So we have we have defined the momentum operator as the generator of infinitesimal translations. Okay. Now we know that the action of this translation, infinitesimal translation operators, on the position eigenkit. Right? We know that it is a translation operator, so it just gets shifted. So we get x prime plus delta x prime. So let me write delta x prime here instead of dx prime. Again, it's just some infinitesimal length. So this is how we define the translation operator, the action of the translation operator. Okay. Now let's look at the action of the translation operator on some arbitrary ket, on ket alpha. Okay. Now we know the action of the infinitesimal translation operator on the position eigenket, right? So to make use of this, let's expand this ket alpha in the position basis. So this can be written as, okay, this can be written as j of delta x prime integral dx prime, and I've got ket x prime, bra x prime, ket alpha. These are the expansion coefficients and these are the basis kets or the basis vectors. Okay. Now this is only an infinitesimal parameter. It's a number with the dimensions of length. So I can take it inside. This is written as integral dx prime. J of delta x prime acting on ket x prime is defined as ket x prime plus delta x prime. So I'll write the action here. Action of j of delta x prime on ket x prime as ket x prime plus delta x prime, and I have got here bra x prime ket alpha. Okay. Now we can just make a change of coordinates and then we can write this as again integral dx prime. So instead of x prime, we can use x prime minus delta x prime. Right? So that will make this as ket x prime and bra x prime minus delta x prime ket alpha. Okay, I've just shifted the origin of my coordinate system by a small amount. Right? So I get it like this. Right? Now what is this? The form of j of delta x prime here? The form of j of delta x prime, we already guessed this is identity operator minus I by h bar, the generator of translations, which we defined as the momentum operator, delta x prime, acting on ket alpha. Okay, so this is what we have on the left side, and this is what we have got on the right side. Okay, so let me find some space here. What we did next is to make a Taylor expansion of this right hand side. All right, so this is some function of x prime minus delta x prime. Okay, so this thing can be written as this function x prime bar x prime minus delta x prime ket alpha. This is some function of x prime minus delta x prime. So we can make a Taylor expansion. We can say this is equal to the function of x prime minus delta x prime partial derivative with respect to x prime of the same function by x prime ket alpha. Alright, so we have discussed this in class. You can check back. Alright, this is how we make a Taylor expansion. There are higher order terms because we are dealing with infinitesimal translations. We neglect the higher order terms and retain only up to the first order term. Okay. Now substituting this here, on the left hand side I have here ket alpha minus I by h bar p delta x prime ket alpha, and on the right side I have got integral dx prime bra x prime. All right, now instead of this thing I am writing this thing. All right, so there will be a term bra x prime ket alpha. Okay, and we can separate these terms again, minus integral dx prime. Here I have got delta x prime partial derivative with respect to x prime of bra x prime ket alpha. Okay, there's also this ket x prime here, sorry, ket x prime. Can this infinitesimal parameter delta x prime can be pulled out of the integral. Okay, now here we see that this is ket alpha itself. This is just ket alpha expanded in the position basis, and on the left hand side also we have ket alpha, so they are the same. All right, so what we are left with is minus IH bar P delta x prime ket alpha is equal to this thing. All right, so we can now equate the coefficients of delta x prime on both sides because the first two terms are equal. All right, the first terms are equal on the left hand side and the right hand side. The first term on the left hand side is equal to the first term on the right hand side. Okay, so we can equate now the coefficient of delta x prime and we get minus IH bar, so minus I divided by h bar P delta. So we are equating the coefficients of delta x prime. So P acting on ket alpha is equal to Again, minus integral dx prime get x prime partial derivative with respect to x prime of bar x prime get alpha. Okay, so this minus goes. What we need is p, so we can multiply throughout by minus ih bar to give p acting on get alpha is equal to minus, I can take it inside, so this is integral dx prime get x prime and minus ih bar partial derivative with respect to x prime of bar x prime get alpha. Okay, now we see that when we are talking about p acting on get alpha, the expansion coefficients are given by minus ih bar partial derivative with respect to x prime of bar x prime get alpha, and we are representing vectors by these expansion coefficients. All right, we saw that get alpha is represented by the expansion coefficients in the position basis bar x prime get alpha. Okay, so looking at this equation, we see that p acting on get alpha is represented by minus ih bar partial derivative with respect to x prime of bar x prime get alpha. All right, so alpha is represented by this, and p acting on get alpha is written like this, which means that the momentum operator can be represented in the position basis as minus ih bar partial derivative with respect to x prime. Okay, so if get alpha is represented by the wave function psi alpha of x prime, right? If get alpha is represented by the wave function psi alpha of x prime, then the state p acting on get alpha, right? This is another get. This is represented. This is represented by minus is bar partial derivative of x prime, partial derivative with respect to x prime of psi alpha of x prime. Okay. So the action of the momentum operator on a state can be represented by the action of this differential operator on the position space wave function, right? On the position space wave function. Okay. So that gives the momentum operator represented in the position basis. The momentum operator in position basis. That answers the first part of our question. Right? So the only thing we did was that we defined momentum operator as the generator of infinitesimal space translations. Okay, so we said that it has to be the Hermitian operator that generates translations in space. Okay, now based on this definition, we saw that this operator should have the form minus ih bar partial derivative with respect to x prime in the position basis, okay, or in the position representation. Okay, so that answers the first part of our question. Let's now go to the second part of the question. Also represent the position operator in momentum representation. Now we have the representation of the momentum operator in the position basis as minus ih bar partial derivative with respect to x prime. Okay. We also have the representation of position operator in the position basis. Okay. This can be easily seen. Let's look at the position operator, the action of position operator on get alpha. All right. We again expand this get alpha in terms of the position eigengets. So these are given by d x prime get x prime bar x prime get alpha. Okay. So we need this operator here. So we can take the operator inside. This is integral dx prime x get x prime bar x prime get alpha. Okay. We have the eigenvalue equation which says that this is equal to integral dx prime x prime get x prime bar x prime get alpha. This means that this is integral dx prime get x prime then multiplied by x prime bar x prime get alpha. Okay, so we see that x acting on get alpha is now represented by this function. All right, x acting on get alpha is now represented by this function. Get alpha itself is represented by this function. All right, when we look at get alpha, this is integral dx prime get x prime bar x prime get alpha. All right, so we take only this expansion coefficients to represent the vector. So get alpha is represented by expansion coefficients here are bar x prime get alpha. Okay, so if you look at the expansion coefficients of x acting on get alpha, the expansion coefficients are x prime bar x prime get alpha. So we can say that the operator x, the action of the operator x in the position space is simply to multiply by the position x prime. Okay, whereas the momentum operator is a derivative. The momentum operator is a derivative. Okay, now we can do the same thing about the momentum space also. Alright, in the momentum space, we can represent the momentum operator, but by this argument, in the momentum space, the momentum operator has to be simply, the action has to be simple. It should be simply multiplying by p prime. Okay, we can just follow exactly similar arguments here, and we'll see that the action of momentum operator on ket alpha, right, has to be simply the multiplication by p prime. Okay, and what about the position operator? This is done. What about the position operator in the momentum representation? What about the position operator in the momentum representation? So for this, without proving, we'll just state the result. The idea is that there's an asymmetry between position and momentum. There's an asymmetry between position and momentum, right? But we could get, which means that we could get x by simply changing p and x, by simply interchanging p and x, right? So we can set x is equal to minus I h bar partial derivative with respect to p prime. Okay, this is almost correct except for this minus sign. All right, so even though it's fairly symmetric, there's no complete symmetry. This can be understood by looking at the commutator. Okay, the commutator of x with p is I h bar, whereas the commutator of p with x is minus I h bar. Okay, so when we interchange all x and p, we'll get an extra minus sign. All right, so that's why we'll get this extra minus sign, and the position operator in the momentum space is written like this. All right, this is I h bar partial derivative with respect to p prime. All right, so this is the momentum operator in the position basis. This is the position operator in the momentum basis. Okay. Now the last part of the question asks us to calculate the commutator of x and p by making use of the operators in the momentum basis. Making use of the operators in the momentum basis. All right. So we saw that x is represented by simply I h bar partial derivative with respect to p prime, and p is represented by the action of p simply multiplying by the corresponding momentum coordinate or momentum value. Okay. So what we need to find is I h bar partial derivative with respect to p prime, comma p prime. Okay, this is the commutator we need to evaluate. Right? But since this is an operator, we can actually talk about it completely correctly only if it's acting on something. So these operators are acting in the function space. Actually, these are acting on the functions in momentum space. So let me write this as phi alpha of p prime. So because we are defining operators by their actions on kets, so in the momentum space, these operators are basically defined by their action on the wave function. Here, it's a momentum space wave function. All right. Okay. Now we can expand this. This is what we need to find. So this is I h bar. We just use the definition of commutator. So this is I h bar partial derivative with respect to p prime of p prime phi alpha of p prime. Okay. Minus p prime I h bar partial derivative with respect to p prime of phi alpha of p prime. Okay, I've just expanded the commutator bracket. Okay. Now I can, so here we see that there's this derivative acting on p prime phi alpha of p prime. So we have to use the product rule, right? Because this is acting on whatever follows here. So we have to use the product rule there. Okay. So applying the product rule, this is equal to I h bar. We have got partial derivative of p prime with respect to p prime multiplied by phi alpha of p prime. Okay. Plus I h bar p prime multiplied by partial derivative of phi alpha of p prime with respect to p prime. Okay, we have just expanded this using the product rule, and here this term just remains like that. So this is minus p prime I h bar partial derivative phi alpha of p prime with respect to p prime. Okay, we see that these two terms are opposite. Right, this is I h bar p prime partial derivative of phi alpha with respect to p prime. Here also we have got I h bar p prime partial derivative of phi alpha with respect to p prime. Okay, so these two terms cancel, and we are left with this is I h bar. The partial derivative of p prime with respect to p prime is 1. So this is simply I h bar phi alpha of p prime. Okay, so here we have I h bar partial derivative of p prime, comma p prime, phi alpha of p prime. This is equal to I h bar phi alpha of p prime. This means that this operator equation has to be correct because we didn't make any special assumptions about this momentum space wave functions. Okay, so this must be like this. This has to mean that the commutator of I h bar partial derivative with respect to p prime comma p prime is equal to I h bar. Okay, or in other words, x comma p, the commutator of x comma p is I h bar. All right, now you could do the same thing in position space also, right? So I leave it as an exercise for you to do this, the same kind of calculation, the position basis, all right? And make sure that this commutation relation is still satisfied, irrespective of the basis. Okay, so if you go to position basis, the momentum operator would be a differential operator, and the action of the position operator is simple, right? So we can use that to find the commutator of x and p using their representations in the position basis. Okay, so I leave that part as an exercise. All right, so with that, I'll conclude this class. Thank you.